Good evening, students. So today let us have a discussion regarding the DC machines. So coming to DC machines, we have two types. One is DC generator and another one is DC motor. DC generator is that in which the mechanical energy is converted into electrical energy. So mechanical energy is converted into electrical energy. So in case of the DC motor, electrical energy is converted into mechanical energy. So coming to any of the DC machine, so given DC machine can be either used as a DC generator or as a DC motor. So what I mean to say is that a DC machine doesn't have any difference as a generator or as a motor. So a given DC machine can be just used either as a generator or as a motor, as it doesn't have any difference construction wise. It all depends upon what type of energy are we going to provide at the input and which type of energy are we going to retrieve from the output terminals. So if the given input is mechanical energy, and if we retrieve electrical energy as the output, we can say that we are utilizing the machine as DC generator. And the same DC machine, if electrical input is given and if mechanical energy is taken, then we can say that it is the DC motor. So now let us see the construction of the DC machine. So coming to construction of a DC machine, it has a yoke which forms the outermost covering of the machine. So within the yoke, we have the field coils, field windings, field poles, and armature. So yoke is the outermost covering. It provides the mechanical support to the machine, and it also holds the field poles to which the field windings are wounded. We know very clearly, if there is a north pole, obviously there will be a south pole. So poles occur in pair, so the number of poles will always be even in number. So just for a sample, here pole machine has been just shown, and this outermost covering is called as yoke. And these are the field poles to which we have the field winding connected to it. So it is these field windings which makes the field poles to act as a magnet and to provide the necessary magnetic field in which the armature rotates. So in general, all the electric machines are made up of electromagnets unless otherwise it is specified as a permanent magnet machine. So if it is a permanent magnet machine, then obviously it will be mentioned explicitly in the title itself. Say for example, permanent magnet synchronous motor, permanent magnet DC motor, likewise. So permanent magnets are very rarely used, and most of the machines are having the electromagnets. What do you mean by electromagnet? The electromagnet is that which will be acting as a magnet on providing the electrical energy to the magnetic material. So these are the field poles, and the winding that is bounded around the field poles are called as field windings. Or called as the field windings. So here if you just see, these field poles are curved at the edges which are called as pole shoes. So the reason for the curved nature of the pole shoes is to spread the magnetism. And we have the armature in the middle. So generally, in any machine, we just speak about two important components. One is called as a rotor and another one is called as a stator. What do you mean by rotor and what do you mean by stator? Rotor is the rotating part of the machine and stator is the stationary part of the machine. In general, in DC machine, it is the field which is acting as the stator. So field is stationary and armature is rotating. So this is true in case of the DC machines, which is just the reverse in case of the AC machines. So in AC machines, field will be acting as the rotor and armature will be acting as the stator. So here, the armature which is present in the mid will be having a shaft and it has the armature slots in it. Armature slots are necessary for incorporating the armature conductors into it. Armature is the housing of conductors. So don't imagine when I say the term conductor such that the conductor to be a solid conductor. So conductor is again a wire which is wounded in a separate fashion. So based upon the way how the armature winding is wounded, it can be classified into two. So coming to the armature winding, it is of two types. One is called as lap winding and another one is called as bay winding. So now we have the shaft in the middle. So when the mechanical energy is provided to the shaft, armature is rotating in the magnetic field. So thereby, the flux linking the coil changes, due to which there is an EMF inducement, and that EMF is a dynamically induced EMF. As the armature is rotating, it cuts the magnetic lines of force, thereby resulting in a dynamically induced EMF, which results in the flow of current. And of course, the current thus induced within the armature conductors are alternating in nature, and it is the commutator which converts the alternating current into DC and provide to the external load circuit. And we have the pair of brushes which are made up of carbon, and the voltage drop across the brush is 1 volt per brush. So thereby, as we are having a pair of brushes, the net voltage drop across the brushes is equal to 2 volt. So it is the brushes which slide along the conductors and collect the current and provide it to the external load circuit. So this is the construction. So let me just recall what are all the important components did we discuss under the construction of DC machine. So first is field poles, field winding, armature and armature winding, so called as armature conductors, and the very primemost component is yoke. Yoke and the brushes and commutator. So it is the yoke which gives a mechanical support to the machine and also holds the field coils. And it is the field poles which hold the field windings. On providing the electrical energy to the field windings, field poles act as a magnet and result in setting up the magnetic field. Armature, which is having an air gap with the field poles, is rotating in the air gap, and the armature is the housing of the armature conductors. So as it is rotating in the magnetic field, it cuts the magnetic lines of force, thereby resulting in a dynamically induced EMF. And brushes are those which slide along the conductors, and it is situated along with the commutator. And commutator is responsible for converting the AC current into DC current, and it provides to the brushes, which conveys the current into the external load circuit. So that's it regarding the construction. Coming to classification. DC machine is broadly classified into two types depending upon how the field is excited. If a separate electrical supply is provided for exciting the field winding, then it is called as separately excited DC generator. If a part of the armature EMF itself is being used for exciting the field winding, then it is called as self-excited DC generator. Again, observing the classification under self-excited DC generator, it is further classified into three types. One is shunt generator, another one is series generator, and the third one is compound generator, depending upon how the field winding is connected with respect to armature. So in case of shunt generator, the field winding is connected in parallel to the armature. So in case of series generator, the field winding is connected in series to the armature. And in case of compound generator, the field winding is connected, both the shunt and series field winding is present. So now let us look at the classification of self-excited DC generator. So coming to the shunt generator, we represent the machine with a circle and with a rectangular blocks on either ends, denoting the brushes. And if we just mention with G along with the solid bar below, it means that it is a DC generator. Then we have the field winding, which is parallel to the armature. Then we have the load connected to it. So within the generator, it accounts for generated EMF and the armature resistance. So this is the field resistance, which is given by RSH. And it is the armature current, which is emerging out of the armature and gets split up into shunt field current and the load current on reaching this middle. So the terminal voltage across the load is V. So now, by applying the Kirchhoff's current law at this node, we can write IA is equal to IL plus ISH. Then taking the generator voltage as the net voltage, it need to meet the value of terminal voltage plus IAR. So this is the EMF equation of shunt generator. Coming to series generator, armature is in series to the field winding, and then it is connected to the load. So this resistance offered by the series field winding is taken to be RC, and the net resistance offered by the armature conductors is taken to be RA, and EG is the magnitude of generated voltage, and this is the load, and the load current is IL, and the current coming out of the generator is IA, and the current that is flowing through the series field winding is ISC, and this is the load. So since it is a single load, IA is equal to IL is equal to ISC, and the voltage across the load can be given by P. So the EMF equation is given by Vg is equal to V plus IARA, which gives the account of armature drop, plus ISC RSC, which gives the account for the series drop. So in this, IA is equal to IL is equal to ISC, thereby the voltage equation can be rewritten as V plus IA into RA plus RC. Now, moving on to the compound generator. Compound generator is that which consists of both the shunt field winding and series field winding. So compound generator is further classified into long shunt compound generator and short shunt compound generator. Long shunt is that in which the parallel winding is parallel to both armature and series field winding is called as long shunt. So the first diagram which is drawn is a long shunt. So you will be able to see that this is the armature and this is the series field winding, which is in series to the armature, and shunt field winding is parallel to the combination of armature and the series field winding. So the current emerging out of the generator is IA, and the current that is circulating through the field winding is ISC. The current on reaching this node gets divided into ISH and the load current IL, and the voltage across the load is P, which is the terminal voltage. So this is long shunt. So coming to the current relationship, IA is equal to ISC and IA is equal to ISH plus IL. And coming to the generated EMF, VG is equal to V plus the drop across the armature conductors IARA plus ISC RSC, which is equal to V plus IA into RA plus RSC. Coming to short shunt, the parallel winding is parallel, the shunt winding is parallel only to the armature, And the series winding is connected in series to the load. So this is RSH and this is RSE. And the current that is coming out of the armature is IA. It gets split up into ISH and IL. And the current that is flowing through RSE is ISE. So in this, the terminal voltage across the load is V. So this is the short shunt circuit. Coming to the short shunt circuit, the current relationship is that IA is equal to ISH plus IA. And IL is equal to IOC. And the generated EMF can be given by VG is equal to IA into RA plus IAC into RSC plus V. So here, the load current is equal to series field current, and the armature current is the summation of shunt field current and the load current. So that's it regarding the classification of self-excited DC generator, which consists of shunt generator, series generator, and a compound generator, depending upon the way how the field winding is connected with respect to the armature. So then, now let us just move on to the DC motor. Coming to DC motor, the working principle of DC motor is that when a current carrying conductor is placed in a magnetic field, it experiences a force. So this is the working principle of the DC motor. And DC motor converts electrical energy into mechanical energy. So again, here we just have the classification as self-excited DC motor, where it has a classification as shunt motor, which has a constant speed, series motor, which has a very high torque, starting torque, compound motor, so coming to the shunt motor, என்ன